afternoon, everybody. Thank you for joining me today, whether you are watching this live or you are watching the recording. I appreciate you all watching. We're going to start talking about analyzing algorithms today, which is our next module, which is, I mean, technically a 2-week module, right? But that's because, but it's almost kind of a 3-week module, right? Because we have spring break kind of thrown into the middle there. So we'll be doing some stuff today, and we'll be talking some stuff on our next live stream, which I think will be the last live stream for this course. It'll be about the same module instead of about something new. So we won't have a live stream next week. We're having this one on analyzing algorithms today, and the Thursday after next, we'll also be talking about analyzing algorithms. And then from that point forward, if my calendar is correct, and this is the calendar that I have in my head, that is the last little bit of class where we'll be working on final projects. So I'll schedule us a little drop-in session just so you can ask questions about your final project and all that kind of stuff. But other than that, that'll basically be it. So another big thing that I want to talk about as an announcement here before we get started talking about analyzing algorithms is when I sent you the link to today's live class. When I sent you the link to this live class to watch it live, right? So if you're watching the recording, it's in the previous announcement. I put a video in there as well. And not only did I put a video in there, but I also put a little Easter egg hunt in there for the Easter holiday season. And these are things that if you find them, they will help you a great deal with your Module 9 assignments that are due today. Right? So especially if you're still working to complete those Module 9 assignments, you might want to go back and have a little look at that previous announcement where I put the link to this live stream to watch it live and put a little more information, a little video and some other stuff that I said might help you with your assignments that are due today. I think they will really, really help if you do that. So with that being said, I think it's time to start talking about analyzing algorithms, and I'm just going to, this module is pretty great because it's no new code, right? Your lab assignments for this module are just like research assignments where you go out and look up answers and answer questions, right? So you've learned all the code that you're going to learn, but I want to talk about how to do it in an efficient manner, in an efficient and effective manner. So we talk about algorithms and analyzing algorithms and their efficiency, and we might not go the whole hour today. We might. I don't know. I have a certain number of slides in the slide deck that I would like for us to get through. And if we get through them, we can stop whenever we are done, right? So might not be as long as normal ones are. But we're talking about analyzing algorithms. And if we remember back to the very first, week of class, maybe that very first live stream, way back in January or the first week of February, we started talking about what an algorithm was, right? And we had these terms that we discussed. And, I showed you the course description, and it talked about algorithms and all this kind of stuff. And I said, well, one of the first things I want for us to do is I want us to kind of demystify the algorithm and take away some of the sort of overly wrought nature of just what this word is. Kind of, take what we normally think about when we hear the word algorithm and make it more approachable, make it make more sense to us. So if you remember way back, two things that we did. One, we talked about the definition of computer science. And two, we talked about the definition of algorithms. Because we had to talk about the definition of algorithms in order to talk about the definition of computer science. We said that computer science is the science of algorithms, specifically the science of algorithms that utilize a computer. Right? So an algorithm itself then is a sequence of steps that specifies how to solve a problem. Now, typically when you hear the word algorithm, you hear it in context with a movie, some kind of news story, some kind of news article. You know, maybe some kind of tutorial video where they're talking about the YouTube algorithm or the Google search algorithm or the Amazon suggestion algorithm. Right? We think about an algorithm as this like big, overly long, complex, super involved math problem that has all sorts of different operations in it in order to find some kind of value or in order to do some kind of thing. And those are examples of algorithms, right? But they're not the only examples of algorithms. Right? An algorithm at the end of the day is just the sequence of steps that specifies how to solve a problem. And, you know, sometimes it's these complex algorithms that, you know, take different values and use them to apply different weight to different items so that it can, you know, recommend things higher in search results, so it can recommend you videos in your suggestion feed, so it can show you related products that you might want to buy. Right? And these can be complicated algorithms, but at the end of the day, it's still just a problem that's been identified. Being able to make people buy more stuff by showing them related items. Being able to make people stay on the site longer by, you know, giving them other videos to watch. Being able to, you know, give people the best search results by recommending the most relevant things highest in the search listing, so on and so forth, right? It's just a problem that people have come up with a way to solve. So in that sort of way, everything that you've been doing this entire semester long has been about algorithms, right? It's all been algorithms. An algorithm can be super simple, right? Like, you know, how do we find an even number? Well, if the modulo of that division problem is greater than if, you know, some number modulo 2 has an outcome has a remainder that's greater than 0, then it's odd. Otherwise, it's even. That's an algorithm. Right? The problem there is how do we find an odd or even number? And so we just took a series of steps there to solve that problem. And so everything that we've been doing, every program that we've been writing for the entire semester has involved some kind of algorithm. Because it was a problem and we took some series of steps and we solved that problem. Right? But what is something else that we've talked about this semester? If I've said it once, I've said it 100 times, that there are dozens of different ways to solve a problem. So for the majority of things that we face, right, and the majority of the things that we do, you know, I would argue that, you know, there were some projects, especially throughout the course of the semester, where each and every one of you got a slightly different solution to be able to answer that problem correctly, as opposed to your other classmates, right? So the question then becomes, if, as we have said in the past, there are dozens of different ways to solve the same problem, is there one that's better? And that's kind of the argument for this module, right? This idea that we do have different things that we can do in order to solve a problem, but some things are better than others. And so really when we face these types of situations, right, we end up with basically one thing, especially as we're getting started, right? Our big goal as we're getting started, number one, is to make it work? If it works, that's tantamount to everything, right? Like, first things first, we want to make our programs work. Once we have a working program, right, we can start to refactor it. And as we're refactoring it, essentially all we're doing as we refactor is we are making it better. So what does this mean for us, right? Because when we think about it in terms of making it work, right, that means that we sat down, we reasoned through a problem, and we figured out a solution that solves that problem. So we have an algorithm. We have a step-by-step algorithm that is going to solve our problem. From there, our goal is to make that better, right? So if we understand the problem and we understand one way that we can solve the problem, maybe we can start to see how we can take different areas of that problem or that problem solution that we've been working on, our program, and make them shorter, make them use less code. Maybe we threw in an extra loop when we didn't need to. Maybe, there was something that might be better off if we held it in a variable just so we could use it in multiple places. Right, we can start to take something that we understand, because if we can solve a problem, that means at least to some degree we understood that problem. So if we understand the problem, we can start to try to figure out better ways to fix it, and that's the whole process of refactoring. So tantamount, number one, the biggest rule is to make it work. The second rule is to make it better. So if we can say that, with certainty that we can make programs better, and that would imply then that there are different algorithms and different ways of doing things that are empirically better than other ways of doing things. So if that's the case, then there has to be some metric that we have that would allow us to understand this. So that metric would be algorithm efficiency. How efficient our algorithm is and what makes an algorithm efficient. So if we can empirically say that one algorithm is better than another algorithm, then what we're saying is one algorithm is more efficient than another algorithm. And this covers a lot of bases. Right? There's a lot of bases that are being covered here. So we have 4 of them here that are examples of different types of efficiencies. CPU usage, which is also called time efficiency or time usage. Right, and this is the amount of time that it takes for your algorithm to be processed by your computer's processor. And this is the one that is our biggest deal here, right? Like, this is the one that we are going to continue to talk about as we kind of go through here. That's sort of the whole thing. That's the one that's most important to us, is the idea of time complexity. But there's also memory usage, which we also call space complexity. And that kind of ties into the stuff we were doing in the last module. How much we need to store in our volatile memory as it's passing things back and forth to the processor to be processed. The disk usage is the size of our program on the disk. And one of the things that's important there is that the size of our program on the non-volatile storage on the hard disk should be appropriate relative to what it does, right? And I think one of the analogies that I gave for this earlier today, right? Because you guys have caught up to the seeded class at this point. I pulled up the add and remove programs dialog on the lab computer in there. And we had to look to see which installation on the disk took up the most space. And that is also a digital media lab in there in 3200 in Paxoy. So it has Adobe Creative Cloud software on it. And so the Adobe Creative Cloud software is notorious for taking up a lot of disk space and a lot of memory space for that matter. And we saw that Premiere Pro, the Adobe Creative Cloud video editing software, took up 3.3 gigabytes on the disk. And when we think about that, that makes a lot of sense, right? Like we are, working with a video editing program. So just on its own, all right, that's going to require a lot of code and a lot of different libraries to work with there. When we start factoring in things like audio and working with audio, effects, various other like codecs, things of that nature, so we can export our video and have it be something that actually functions. Right? There are all sorts of things that, we could do with this program. So when we think about it in that sort of way, right, 3.3 gigabytes isn't so bad compared to what it can do, right? Like if I had just a simple notepad that took up 3.3 gigabytes of hard drive space, that would be a huge issue, right? And we could do that if we were ineffective with our disk usage and being mindful of the code that we use, right? Like that's why, that's part of the reason why we have to, import libraries when we want to use them, because they're not imported by default. If we had all of these libraries that we don't use every time in our program, that's going to add disk usage space, and that's going to make our program bulkier than it needs to be. And then network usage, making sure that, if you have a program that communicates across a network, making sure that it is utilizing network usage properly. When you are sending too much traffic across the network, which could be something that happens. Right? You can create bottlenecks, you can, basically kind of DOS attack your own, your user's network, whatever network they're on, if you're sending out too much data, or you're not sending it out at the right intervals or things of that nature, right? So all of these things are different types of efficiencies. But for our purpose and what we're going to be talking about over the next couple of weeks, we're going to primarily be focusing on time complexity or time usage, which is our CPU usage. Now, as we're talking about time complexity, it's important for us to understand that when we say time complexity, we're not talking about a certain amount of time. Because time complexity is relative. And this gets us into the difference between performance and complexity. Performance is dependent on device, right? What kind of hardware a device has in it, what type of compiler might be installed on that device to run your code, and so on and so forth. Performance is device dependent. A program that runs poorly, that performs poorly on one machine could perform fine on a machine with better resources, more RAM, a better processor, so on and so forth, right? One of the things that we were talking about in relation to this is video games, right? When we think about different video games and what different video game systems can handle, some of them physically can't handle some of the more complex things that we're doing nowadays. But if you look at the performance on a PC versus the performance on a console of what is the same game, you can see that one, typically you can see that one works a little bit better than another. And that's going to all be dependent on hardware. Complexity, on the other hand, is relative. Complexity is relative time. How the resource requirements of a program or algorithm scale. So we're looking at kind of what happens as the size of the program being solved gets larger. Right? So if I'm sorting a list of 10 words to put them in alphabetical order, my computer might do it in an instant. Right? A super fast computer might do it in an instant. If I'm sorting a list of 10,000 words in alphabetical order, it might take some more time. It probably will take several seconds in order to do that. Right? But the amount of time that it takes is relative to the resources that the machine has. A fast computer still might get it done within a couple seconds, whereas if you have a really slow computer, right, to sort 10 words, it might take a second or two, and then it can take up to a minute or more to sort a bunch more words, right? The complexity scales based on the hardware requirements, and the size of the problem that's being solved. So what we see here is that complexity impacts performance, but performance does not impact complexity. Because we can basically say that performance is an external factor. Complexity is internal. Performance relies on external factors in order to happen. So when we say that, just how long does it take to execute an algorithm? Or just how long does it take for an algorithm to execute? And it is, again, proportional to the number of basic operations that it performs. And we've been doing basic operations all summer, right? We've been doing arithmetic operations. We've been doing, variable assignments. And if you look there in that second lower bullet point, that colon equals, that is called a walrus operator, which is something that we don't necessarily teach in this level because it's kind of outside the scope of what we're doing. But it is it is an interesting little operator in Python there. Testing code, which that should be equals there. X equals 0 to return a true or false. So I accidentally left out an equals sign there. Reading some primitive, writing some primitive, like an integer, a float, a character, or a Boolean, right? Each of these individual things is one operation and adds to the amount of time in terms of complexity that it takes to solve a problem. But you might notice, right, especially as we kind of advance technologically, we do one of these basic operations, it's performed instantly, right, in a blink of an eye. And when we examine multiple of these operations, as long as they're basic operations, they're still happening within a blink of an eye. Right? Because what we see is our computer, especially nowadays, processors have multiple cores, 8, 12, 16 cores, and there's multi-threading in those cores, so they can process multiple problems at a single time. Right? So multiple things are happening in an instant. So if we can say that multiple basic operations can happen in an instant, what is one of the best ways for us to kind of gauge how long our algorithm takes to run? And that's based on the worst case scenario. So the worst case scenario basically just says, what's the maximum number of operations that might be performed for a given problem size. That's the worst case scenario. And so this is the number that we're going to use to kind of determine our complexity. Is this worst case scenario? The maximum number of operations that need to be completed for a particular problem size. So say, for example, we're just taking a list and we're going to append an element to it, right? We're going to insert an element to a list. What we have to do when we do that is we have to move the current element and all of the list elements that come after it one place to the right. And so this is an insertion and not an appending, right? So like if we insert a new thing at like index location 0, it's going to take everything else and move it down the list. If we append it, it's a little simpler because we just append it to the end of the list. But if we insert at the beginning of the list a new item, we have to take every other list item and move it one place to the right in the list. So in the worst case scenario, inserting at the beginning of the list, all of the other items in the list have to be moved. So that's one operation to move each of the items in the list, and another operation to add this new spot into the list. So we can say then that the worst case scenario for the time for insertion is proportional to the number of elements in the list. And so we say worst case time for the insertion operator is linear. This is linear time in the number of elements in the list. So this would be in big O notation, which we're going to talk about in a moment. This would be O of n. O(n). N here representing the number of items in the list. So for a linear time algorithm, if the problem size doubles, right? So if there's twice as many numbers in our list than it was previously, the number of operations also doubles, right? Because we have, now we have twice as many numbers in our list, so we have to move twice as many numbers one space to the right before we insert that final number. Right, so our linear time algorithms are just going to keep growing. Now, when we talk about O notation, big O notation, that's still going to be O(n), right, even though the problem doubled. Because n still represents all the numbers in the list, right? So one of the things that we just want to keep in mind here is that when we're talking about time complexity, we are not talking about a set amount of time, right? We're just talking about the amount of time that needs to be used relative to the operation that is occurring. And so we represent these worst case scenarios, we represent them in big O notation. Big O notation is an expression of complexity. So what I would like to do is just take a few moments here and look at our different big O complexities using cake. Colleague of mine, their birthday is today. They had some cake in the break room. I didn't get any, but other people did. So, it's kind of appropriate to kind of look at the idea of complexity here in relation to birthday cake. I think it kind of helps us understand and kind of wrap our heads around the situation here. So the first thing that we have here is O1. O1 is constant time. So for constant time, no matter how many people come to the birthday party, you only make one cake. So no matter how many things we bring in, we only have one operation that we need to do to complete our job. That's constant time. So the cake making time stays constant. Right? We can compare that to linear time that we were just talking about, where as we're inviting more people to the party, and we'll talk about this more in just a little bit. As we're inviting more people to the party, we have to do more operations and bake more cakes for each person. So in our constant time situation, regardless of the length of our array or whatever we're working with, right? We're only doing one operation, a singular operation to complete the job. Right? The cake making time remains constant. That's why it's constant time, right? It takes the same amount of time to do it with a list that is one number long as it does with a list with 1,000 numbers in it, right? Then we have logarithmic time. For the logarithmic time example, the birthday cakes are kind of used to incentivize people to turn up to the party on time. Right? And so this is a little bit harder to kind of wrap our heads around when we do our next when we do our next lesson on this stuff. We'll talk more about like examples in which our output is logarithmic time. But essentially what we're looking at here is the first person to arrive gets a cake that's all to themselves. Then the next 2 people to arrive share a cake. Then the next 4 people all share a cake, and so on and so forth, right? So we can look at things like merge sorts, different types of sorts here for that. Again, we'll talk about code examples next time we do this. So in over a week's time, we'll review really quickly, and we'll look at some code examples. So a 1-person party requires 1 cake. A 2 or 3-person party requires 2 cakes. A 4 to 7-person party requires 3 cakes, so on and so forth. So the more people that come to the party, the more cakes we bake to accommodate this list, or these number of people. Right, but it's not a 1-to-1. It kind of, you have one that can handle multiple things. And so we, if my math people out there, an n number person party, n being just a variable for whomever, however many here, right, requires the log of 2 times n number of cakes in order to reach that complexity. So we can see that depicted graphically here. And this is O log of n. So we can see we're not directly scaling our cakes with our number of people, but we are increasing the number of cakes with the number of people. So this is more complex. This would be more complex operations than constant time, because constant time is 1 cake regardless of how many people. Right? And we're thinking about the cake here in terms of like time spent on baking the cakes. Now we have our friend linear time, and so we can see, right, as we talked about previously, linear time, each guest gets their own cake. So each person that comes to the party gets their own cake. So there's 1 cake for each person that's there. So if there's 1 person there, there's 1 cake. If there's 2 people there, there's 2 cakes. If there's 100 people there, there's 100 cakes. Right? So we can think about that in terms of the list that we just talked about, because we said that was linear time. Right? So if we have a list that has 1,000 items in it, and we want to move each of those items 1 space to the right, so we can add an item to the beginning of our list, then each of those items gets an operation for complexity. That's linear time, right? We're giving an operation for each item. Next, we have quadratic time. Quadratic time is O(n) squared. For the quadratic time example, each guest has their own cake, but in addition to each guest having their own cake, the names of all of the guests are written on it. So not only have we taken time baking these cakes, but we've taken extra time to take and write in icing on all of the cakes everybody's name that's there. So we write everybody's name that's there one time for every one cake that we make. And so one thing that we could see here is like a nested loop, right? Like let's say we are nesting a for loop that's going to iterate over an array twice, like a bubble sort, right? So for each iteration through the array, we're going to iterate over the array, basically. Iterate over the list. So for each iteration over that first iteration, we're going to do a complete whole second iteration. That's what we're talking about here. Right? We're adding that extra time that it takes. You know, we're adding an entire party's worth of operations per each operation. So it's a squared number of operations. Our bubble sort is one, right? And so we can see that example here. Right? Instead of cakes here, they've put little scribbles on the top to represent the names. And we can see on the first cake there, it has one little scribble. On the second set of cakes there are two little scribbles, so on and so forth. And, you know, for each other person that we add to the party, that adds even more work. And so when we compare time complexity in that sort of way, and this is the last slide I want us to look at today, we see this. Right? As the number of party guests increase, or the number of items in our list, the number of operations that we're doing increases, we see how this increases complexity. Right? We see our linear time. There's the green line in the middle, that diagonal line. As we add, since it is linear time and it is, you know, one operation per one thing, we can see that it's on that upward trajectory there. O1, our constant time, that's the least complex, right? Because it's just one doing one thing regardless of how many people are there. O of log n is a little more complex. O of n squared, a little more complex even still. And finally, we have one that we didn't even talk about here because it's, you know, it's kind of rare. That's O of n factorial. And that's the most complex that we would be dealing with. And so when we go through these in the future, what I'd like to do is I'd like to show you examples of different types of code and talk about what makes this different type of code, these different types of code, to have whichever one of these time complexities, whether it's constant time, logarithmic time, linear time, so on and so forth. So that's all that I have for you for today. We're going to go ahead and stop here. That's all that's the last slide I wanted us to do. I said once we got to the slide where I wanted us to stop, we were going to stop. We'll turn the music back on for just a couple minutes, just in case anybody who is here watching live has any questions. Thank you for watching. Have a great spring break. We'll see you next time.